In this lesson, we're going to study ionic radius, which is a similar idea to atomic radius, but of course, it's going to be the radius of ions, and we'll need the octet rule to help us understand that, and we'll also look at metal ions versus non-metal ions. We'll even compare atomic radius to ionic radius, and we'll even compare different ionic radii. So there is a bookwork associated with this lesson. We're going to do the odd-numbered questions, 1 through 25, on pages 83 to 85. This should be written down on a separate piece of paper, which will go in the classwork section of your binder. Our aim is how does atomic radius change when atoms become ions? And please copy down these questions, put them on that same piece of paper that you're going to write your homework on, and this will go under classwork in your binder. And ultimately, we'll have a pair-up and a summary there as well. But copy these down and we'll do those in class tomorrow. So the octet rule. You've probably heard the word octet before, and if you haven't, it has to do with the number 8. Like an octopus, for instance, has 8 legs. But the octet rule is a rule that has to do with 8, and basically it says that all any atom ever wanted was a completely filled outermost orbital. And in chemistry, this orbital is named the valence shell, and the valence shell has, you guessed it, 8 electrons in it. So here's a question. It says, how many electrons would it take to fill the valence shell of an atom in the first period? So if you're an atom in the first period, that means that you're either hydrogen or helium. And they only have one orbital, and the first orbital can only hold 2 electrons. So since the first orbital can only hold 2 electrons, and hydrogen and helium only have one orbital, then we know that it would take 2 electrons to fill the valence shell of an atom in the first period. So when I look at this number 8 up here as the number of electrons needed to fill the valence shell, then it only applies to elements that are not hydrogen or helium. So hydrogen and helium, the answer would be 2 there. So it says, how many electrons would it take to fill the valence shell of an atom in period 2? Well, in that case, the answer is going to be 8 electrons, because if you're in period 2, then you have 2 orbitals, and the second orbital can hold 8 electrons. So you might be thinking that it would take 18 electrons to fill the valence shell of an atom in period 3. And although that's actually a really good way to think, it turns out that it isn't true. You can just use your periodic table to quickly confirm that. All the elements after helium have an 8 to fill their second orbital. So besides period 1, all atoms have a completely filled valence shell when the outermost orbital contains 8 electrons. This is a really important idea, so don't forget to write that down. Okay, so when we compare metal ions versus non-metal ions, we need to be considering their valence shells. So if an atom has a partially filled valence shell, the fastest path to filling could be in either of 2 directions. You could gain electrons to get to 8, or perhaps you would lose electrons to reveal the orbital beneath. So here are some examples of what I mean. Let's take a look at elements from period 2. Here's lithium. And lithium has, it has 1 electron in its valence shell. That means the easiest thing that it can do to reveal a filled orbital is actually to drop that electron. So it's not in every case that an atom will gain electrons until it has 8. In this case, the atom lost an electron so that it would have 2. Moving on to beryllium, I'm going to say that it's going to be a very similar idea. This guy is going to lose 2 electrons in order to reveal a full orbital of 2 for orbital 1. Moving on, boron, whose configuration is 2,3. This guy's going to drop 3 electrons And when it does so, it's going to reveal an orbital, a full orbital of 2 electrons beneath. For carbon, this is where you're going to notice a switch. So remember, for this orbital, orbital number 2, you can hold 8 electrons. And 4, of course, is halfway between 0 and 8. It is true, carbon could either gain 4 electrons or lose 4 electrons. The question is, which one will it do more often? And as it turns out, you can tell by the ion charge here of -4 that it's gained 4 electrons. So most carbon atoms will gain 4 electrons. Some will lose 4 electrons, and you'll have to rely on the specifics of the individual question you're looking at to know which has been the case. But in this case, carbon gained 4 electrons so that it now has a configuration of 2, 8. If we look at nitrogen, I think you're going to notice something very similar. It's clearly going to gain 3 electrons, and in doing so, it's going to get a new configuration of 2, 8. Going further, oxygen will gain 2 electrons, and in so doing, it will have a new configuration of 2, 8. Fluorine, as well, is going to gain 1 electron to get a new configuration of 2, 8. And lastly, neon is going to gain no electrons. And the reason for that is that it already has 8 electrons in its second orbital, and that's the number that atoms want. So what is an ion? An ion is an atom that has gained or lost electrons and has a charge. Examples could be lithium +1 ions, nitrogen -3 ions, or even chlorine -1 ions. So atoms can gain or lose electrons, and if they gain electrons, of course, that's going to give you a positive charge. Oh, and here, did you notice I didn't write the 1? That's because when you have an element whose charge is +1 or -1, you don't have to write it. So I just went ahead and added it in. But +1 means you lost an electron, -3 means you gained 3 electrons, and -1 means you gained 1 electron. All right, are metals more likely to lose or gain electrons? Metals are definitely more likely to lose electrons. And the reason for that is because metals like lithium and beryllium, they only have 1 or 2 electrons in their outermost shell. Therefore, it's easier to lose an electron for sure. So similarly, since nonmetals like oxygen and fluorine already have at least, let's say, like 6 or 7 electrons in their valence shell, it's much more likely that they'll gain electrons when they become ions. So I recorded that information. Let's move to the next slide. Atomic radius versus ionic radius. So if atomic radius is the radius of an atom, then ionic radius is the radius of its ion. And the radius of an ion actually could be bigger or smaller than its element's atomic radius, and it all depends on how that atom came to be an ion. So to become an ion, an atom could do 2 things. It could gain electrons, as is the case usually with nonmetals, or it could lose electrons, which is the case typically with metals. So if an atom is to gain electrons, the ion's radius, so that's after it's gained the electrons, if an atom is to gain an electrons, the ion's radius will be larger than the atom's radius. and that is a result of an increase in repulsion between the new electrons. And if an atom becomes an ion by losing electrons, then as a result you can expect the ion's radius to be smaller. And part of the reason for that is that you're losing electrons and there's a reduction in the repulsion between electrons. But also, and this is typical, when a metal ion loses electrons, it tends to lose a whole orbital to reveal a new orbital beneath. So it's possible that that would be the major reason why that an ion for a metal would be smaller. So as a recap, metals form ions that are smaller than their original atomic radii, and nonmetals form ions that are larger than their original atomic radii, and I'll put in my fast reasons for why. So that brings us to the end of the lesson. Please just copy down this pair up underneath the do now for, I guess you already copied down the do now, so just copy down this pair up under the do now, and also copy down this summary under the do now, and under the pair up, and we'll do these in class tomorrow.